Hello, good morning, everyone. Today, inshallah, we will continue our search for optimality in the case of having an inequality constraint or inequality constraints relative to a certain problem. Of course, all of our course notes, recorded sessions, and everything, you will find them on Moodle. Also, the recorded lectures, you will find them all on the YouTube. Please watch them carefully and try to be, while watching these videos, having just only, as I usually do, a piece of paper beside you and your pen ready with you and start to check all the information that we will go through. That's really the main key for being able to understand and to collect all the information. Another remark, please don't skip any information or hesitation about certain statement or about something need to be checked from the previous sessions. Make a stop, go through it once more from the previous videos, then try to continue in order to get the maximum of your session. Once more, this is our landscape. And finally, today it is our last lecture in this journey, which is going to be really very interesting lecture. I would please ask you all just to focus and to go through it step by step with us. We will see today, in the previous session, we already spoke about how to form the Karushkhuhn Tucker conditions for a certain optimality problem. Now, successfully, from the previous session, we know how to write the KKT conditions. I told you. Now, we can use the KKT to determine the maximum optimization or points and the extremum of these problems. So we will see the solution here, inshallah. Once the problem is solved, we can analyze for the future development or the what's called the sensitivity analysis. So as you can see, from now, let me get my laser pointer first. Okay, as you can see, we can use the KKT to determine the extremum points. Within this session, we will see this, and it's really very nice and logic steps that we will follow. Once the problem is solved, we can analyze how the optimal changes when any of its parameters is changed, which is called the sensitivity analysis, one of the most important analysis after solving an optimality problem. Of course, this part will help us in expecting what's gonna be the new resolutions due to certain change of a parameter without resolving the problem. I spoke about this previously. It's not that easy to solve once you got the optimal solution to resolve your problem, because in some situations the problem size is massive, plenty of constraints. The Karush-Tucker is a bunch of inequalities and equations working together. So trying to do this once more from scratch, in plenty of cases, it's really very difficult, time exhausting. So we need to understand how to develop our model perfectly without going to this aspect. So let's see how to do the solution of the KKT system. Of course, the set of or the solution set will need the following. Number one, KKT condition of an optimization problem is a system, as you remember from the previous session, and we will go through these problems once more. I will try to make a recap of how to do the KKT conditions, and in order to fully understand that the system of KKT is inequalities and the equations, which may be solved using the following. Number one, some information obtained from its graphical resolution. So you need to look carefully about the objective function and the constraints. Maybe I have some information from the graphical resolution. If we can obtain additional remark that will help us greatly, and we will see an example while we are trying to seek another piece of information that will make our life easier. By the idea, before we continue, this session is really very important. It will be involved in your final exam, so I need you to listen to it carefully and try to go through it step by step. Once more, if we can obtain additional remarks that will simplify the KKT system from this information. Number two, maybe a hunch. Maybe I need to check that if x is equal to 0, is greater than 0, what's going to be the resolution at this case, which is just only a hunch. But a hunch will lead to points that need to be checked at all the systems satisfying all the KKT conditions. That's what we are talking or what we mean by a hunch. Okay, the last option for us is to try to go by trial and error, considering different scenarios for each variable until we can cover all the possible cases as we would say. In order to play with all of this, let's back to our reference problem, the problem that we initiated 2 lectures ago, which is a very simple, well constructed problem. Let's consider the maximization problem of x squared plus y squared, which is subject to these constraints. Please read the constraints carefully. It's an x is greater than or equal to 0, y is greater than or equal to 0, and we did spoke about this previously, the non-negativity constraints, which ensures that your decision variables are touchable, are something you can deal with. They are with positive values. Then also we have the third constraint, which states that the sum of the both decision variables is less than or equal to 2. So now we have 3 constraints. The 3 constraints together, or some of these constraints, which is the inequality constraint, plus the objective function, will help us in building the Lagrangian function, which we will depend on in performing or in doing our KKT inequalities and equations, as we will see. Once more, how to form this Lagrangian function? It's really very simple. All I have to do is to take the objective function, as you can see, we'll insert it first, then plus lambda, which is a value greater than 0, greater than or equal to 0. Then we will move x plus y to the right-hand side. So I will have 2 minus x minus y. I don't want to go through how to move the x plus y to the 2 side. We will we will remain with this operation as it is in order to avoid any misleading signs or sign conversion. So all we have to do now is just to move x plus y to the other side or to the right side plus 2. So it's going to be 2 minus x minus y, as you can see. Now, the conditions of the KKT. We already stated this previously, but I will refresh it with you once more. Since the first constraint is greater than or equal to 0, so the derivative of the Lagrangian function with respect to x is going to be less than or equal to 0. So all I have to do is to differentiate what I have greater than or equal to 0. I will have the derivative of the decision variables less than or equal to 0. And I have x is equal to greater than or equal to 0, and the multiplication of x times the derivative with respect to x is equal to 0. As you can see from the first constraint, which is x greater than or equal to 0, we have 2 inequalities and 1 equation. Once more, 2 inequalities and 1 equation. The 2 inequalities by themselves, one of them you already know, which is the condition by itself. The other one, wrote to the sign. It's x greater than or equal to 0, then of course the derivative will be less than or equal to 0. I want this to be tightened into your mind, especially at this case. If you need more information about and why the inequality signs and changes and everything, You will find them in the previous session. But for the time being, let's get pragmatic and go step by step. So for y is greater than or equal to 0, it's exactly the same. That's the second non-negativity condition, which also will give us two inequality constraints and one equation. The first is y is greater than or equal to 0, and the derivative of the Lagrangian function with respect to y is going to be less than or equal to 0. Yes, I want you to remember this. More than or greater than or equal to 0 for the non-negativity constraint will lead to less than or equal to 0 for the derivative of the Lagrangian function. That's the simplest way as it is. Multiplying these two together, you will have your equation. Now coming for the last constraint, which is x plus y is less than or equal to 2. In this case, I will try to make the derivative with respect to lambda. So differentiating with respect to lambda will develop that lambda dash is equal to, the derivative with respect to lambda is going to be greater than or equal to 0, which means this constraint you will have to obey. That's x plus y is less than or equal to 0. Remark the first inequality and this constraint form, they are the same. So if you make the derivative, it will lead you to 2 minus x minus y, which is greater than or equal to 0. Moving negative x and negative y to the other side will give you the constraint. Then lambda is greater than or equal to 0 by definition. The multiplication of both of them will equal to 0. All of this and the details of evaluation or constructing the KKT condition, you will find them in the previous session. Now, how I'm going to continue. So I will start differentiating with respect to x, the Lagrangian function. I'm writing the first inequality within relative to the first line. So it's going to be derivative with respect to x is going to be 2x. Differentiating with respect to x, this guy will develop minus lambda, and it's less than or equal to 0 from the KKT conditions. The next step is x is greater than or equal to 0. That's the second inequality. And for the equation, x times 2x minus lambda is going to equal to 0, which is beautifully written. In a similar manner, I will go for the second row. Differentiating first with respect to y, putting the condition that y is greater than or equal to 0. The multiplication of both of them will equal to 0, as you would see. So let's do it once more. Differentiating with respect to y, it's going to develop 2y, then minus lambda, okay, because y is going to be 1, negative 1 times lambda is going to be negative lambda. The inequality is from the KKT, the KARUSHKUHN TUCKER, which is less than or equal to 0. And for y is greater than or equal to 0, and for sure the multiplication of y times 2y minus lambda is going to equal to 0. In a similar manner, for the lambda, I will start differentiating the Lagrangian function with respect to lambda, giving us the condition or the constraint in form, exactly the same, x plus y is less than or equal to 2. And for lambda is greater than 0, as you can see. And then finally, I will go for the multiplication of lambda times the first equation, which is going to be the third one, as you can see. Now I have the system, which is 6 inequalities and 3 equations. It's really a very good idea at the time being is to label them. So I'm taking for the columns A, B, and C sets, and for the rows 1, 2, and 3. This how I can get to any of these inequalities or equations very simple. So if I see 1C, I mean x dot x minus lambda. If I said 3C, which means the third row in this equation is specific, which is lambda times 2 minus x minus y, and we will use this knowledge in hacking this system of inequalities and equations. As you can see, we have 6 inequalities and 3 equations, and we are hopeless at the time being. How to start tackling this system, complicated system, which is a bunch of inequalities and just only 3 equations. We remark that without an additional information, we cannot solve this KKT system. We know that x is greater than or equal to 0 and y is greater than or equal to 0. So let's get some assumptions and get smart and try. Hopefully we will get lucky and we will get suitable solutions. I will start with x is greater than or equal to 0. For this condition, x is greater than or equal to 0, I will bracket the x is equal to 0 first, and then I will see what's gonna be. So case x is equal to 0. Okay, this is gonna give me, if I have x, y, and lambda, a plan, which is in y and the lambda. All of these points are possible solutions, but I will need to reduce this once more. So I have y is greater than or equal to 0. Let's take first the case of y equal to 0. According to these assumptions, I'm trying to see what's gonna happen. If x is equal to 0, y equal to 0, is it gonna lead to a suitable solution for this system or not? So considering these 2 points or these 2 remarks together will lead to, we have possible values of lambda. So all I have to do is to look to my inequalities and equations. Exactly. As you can see, I'm looking at them very closely. Okay. I can go to 3c, 3c, which is lambda dot 2 minus x minus y. Putting x and y equal to 0 will lead to the only solution that it is lambda equal to 0, because you will have 2 times lambda and it's equal to 0, leading you to lambda equal to 0. Now, for the solution of triple zeros, I have the value of x equal to 0, the value of y is equal to 0, and the lambda is equal to 0. Let's move to the next slide. Okay, that's the results we reached. X 0, y 0, and lambda becomes 0. So now we need to discuss this solution. Is it a possible solution for all of them, for all of these equations, or not? How to check that? I would recommend that we will check each one of these inequalities and equations and be sure that it's correct. Because the ones that involved in our solutions are 1b, 2b, and 3c. This is 1b, which states that x is greater than or equal to 0. We take advantage of this inequality. Y is greater than or equal to 0. Take also advantage of this guy. And finally, for that's 3c constraint that we used this guy in order to continue and get the value of lambda. I will take this solution and I will make this table, which summarizes the cases. I will take the solution 0, 0, 0, and I will check it with each and every part of these parts of the inequalities system. And here is the result. It is all correct and satisfied. Now, for this, after substituting in the whole table now, we are sure that triple zero is satisfying the whole system of equations. Remember, we studied just only the case for x is equal to 0. Let's do all of this once more when x is greater than 0. But before going through this, remember also we studied just only at y equal to 0. So I will need to check if y is greater than 0 is gonna make another resolution or not. Okay, if y is greater than or equal to 0, let's go to 2c. The equation at 2c, okay, which is for y is greater than 0, we will have the only solution that's 2y minus lambda equal to 0. So if I went to 2c, I will get 2y minus lambda equal to 0, which leads that in the lambda equal to 2y, and y is greater than 0, then lambda is greater than 0 from this equation. So now I'm sure that y is greater than 0, lambda is greater than 0. Let's go for 3c. If we went through 3c, that leaves us with just only 2 minus x minus y equal to 0. Remember that we started all of this with x equal to 0, still apply here. So we will have 2 minus y equal to 0. That's y is gonna equal to 2. Once we know the value of y, we will be able to get the value of lambda from here. So y is equal to 2, making the substitution, as you can see. So we'll leave you with lambda is equal to 4. Now I have the value of y, the value of lambda, so I will be able to get and have the value of x, of course. So now x is equal to 0, y2, lambda 4, which is a probable solution for this system once more. How to be sure that it is satisfied? All I have to do is to regain my table once more with the ABC, the numbers 1, 2, 3, and I will check each inequality and the equation that exists in this table. So once more, I will do all of this, checking all the inequalities and equations, and it is all satisfied. So we are in a very good shape. Now, once more, here is the system. And let's study now the case of x is greater than or equal to 0. And as we did previously, we'll consider x is greater than or equal to 0. I will go for 1c, which implies that 2x minus lambda must equal to 0. That's lambda equal to 2x. Okay, in a similar manner, lambda is equal to 2x, which means for x is greater than 0, this will develop lambda is greater than 0. So once more, taking this note and going to 3c, I will have 2 minus x minus y equal to 0, which leads us that we can get one of these decision variables on behalf of the other. So I can get x equal to 2 minus y. Now I have x 2 minus y. I will use the values of y. If y equal to 0, that's x equal to 2 directly. So which means lambda equal to 4. So I have another winner, which is 204, a probable solution for this problem. Let's do it once more and check all the 6 inequalities and the 3 equations in the table. It's all satisfied. In a similar manner, in the case of y is greater than 0, I can take advantage from 2c, which is gonna let us to 2y minus lambda equal to 0. That's lambda equal to 2y, as you can see. Now, I know already x is greater than 0, so lambda is equal to 2x. I wrote it to you as a notation here from where it came. So now I have 2x equal to 2y, so y and x is equal to each other. Once y and x is equal to each other, now we can go to exactly like previously, making the substitution with 3c, which is going to develop that y is equal to 1. Once we know the value of y, we knew the value of x, we both of them, we know the value of lambda. So now we have the winner here, which is 112, and it's also checking the system, it's all satisfied. So at the time being, from all of this, we have 4 candidates for this problem, which are, or the optimization problem, we have 4 solutions for this KKT conditions, which are the 000, 024, 204, and 111 as maximizers for this problem. Okay, this is also one of the magnificent problems, or one of the real life situation, an answered problem, and the open questions that's maybe involved in your exam. I believe it's gonna be within something like this. It's a scenario. It's as you will see, it's just only a series. You will have to go through it, explaining the situation or explaining a real life situation and what's going to happen. So once more, here is stating to you, in a sports club for 3 directors, Luis, Pedro, and Paulo. And this example from the main slides, it's really very nice example. So once more, in one of the sports clubs, you have 3 directors getting together in a closed meeting. As you can see, doors are closed, weapons are ready, and they are trying to see a probable solution to guarantee their winning and with maximum points, as we will see. So the guys talking to each other, Laos, Pedro, and Paulo, had a meeting discussing the current situation. As you can see, it's lovely meeting as usual. The nature of these meetings. Laos, no need to ensure we will need the next championship. Guys, we will need to win. Pedro, our team may not have enough quality for that. We are not sure about our winning case. Paulo, he will start talking, the smart guy here, how to play the cards. So we have to hand out vouchers to referees, send emails to people in power, and debate players of other teams. So here we go under the table and see what we can do to make our life easy in matches. So this is the three possible solutions or the three possible ideas of our directors. So Paulo uses these strategies before, so he has some data about it. Number one, we can consider number of vouchers, which is X as we did previously. The cost of each one of them is going to be 1 million euro. And the benefits as points, it's going to be 2 minus x, negative 2 minus x plus y, minus z, as you can see. That's going to be the benefits, depending on the x, y, z, considering x once more, the number of vouchers. Number two, we can set number of emails for people in power. The cost of these emails will be 2m, and the benefits will be 4 minus x plus 2z extra points for us. We can also go to the number of players or sum of the players, which is stand for Z, and give 3m for each. The benefits would be 6 plus x minus y minus z extra points. This is how we played this previously, and this is how to continue. I'm just trying to go with the system here and trying to give some drama about this series. Paulo add that for these strategies to work, and this is need to be read very carefully, the total budget should be 15m. So that's a constraint. That's an appearance of constraint. And the number of emails and the players should be greater than 6m. And finally, to avoid suspicious, the number of vouchers should exceed 3. The goal of the director is to get the maximum number of extra points. That's stop. These live problems will need to be read at least from 3 to 4 times. You will have to read them from 3 to 4 times at least in order to speculate what I'm going to give you. I myself, for this problem, when I read it for the first time, I did go through it 3 times, 4 times, I believe so, in order to be sure that I didn't miss any information or hidden piece of data within the lines. Number one, what we came out of all of this or of this scenario, that the money available for the strategies is 15. Number two, okay, that the condition for these strategies to work is the number of both the emails and the number of players should be greater than or equal to 6. The other condition is for the secret of the strategy, the number of just a second, vouchers, I'm sorry, is less than or equal to 3. Okay, once more, the goal of the directors is to get the maximum number of extra points. Now, how to translate all of this and formulate it together to get the required mathematical model. So let's formulate this problem for the time being. Now I have X number of vouchers and the cost is 1. The benefits is known. Number of players, which is Y. The cost and benefits already known. Number of players is Z. And the cost and the benefits is already known. The optimization type for this problem, we need to maximize the benefits, the number of points. The social variables that I have is X, Y, and Z, which represent the 3 strategies. So the maximum number of extra points. Let's remark how we are going to formalize our optimization problem or the objective function. Okay, I now I'm needing to maximize the number of extra points. The number of extra points will come to me from the benefits of these three strategies. So all the benefits that's coming from the number of vouchers, it will be simply multiplying X times the benefits of these extra points. So it's going to be X times -2 minus X plus Y minus Z, as you can see. So multiplying the number of vouchers times the benefits will get me the total number of benefits that I need. In a similar manner, I will multiply the number of emails times the number of points of these emails. And now I have this strategy overall number of points. In a similar manner, multiplying the number of players times the benefits from recruiting these players, which is going to be the third part. So trying to shave some things a little bit and gather the numbers together and reform it and put it in a beautiful objective function shape. So it's going to be negative x squared, as you can see, negative z squared, and these are the various numbers already exist, or the various parts. Now for the constraints. I have a constraint on the budget. I have a constraint on the number of non-negative. Of course, before all of this, we have non-negativity constraints because X, Y, and Z, they are actions. So it can't be negative. Then I have an inequality constraints regarding G1, which is less than or equal to 1. That's the budget, which is less than or equal 15. Y and Z must be greater than or equal to 6. And of course, the number of vouchers must exceed 3, which is must be less than or equal to 3, as we can see. So that's the objective function subject to this set of constraints. Now we formulated our problem. So as you can see, we have 1, 2, 3, 4, 5, and 6, which means we will have 6 rows from the KKT conditions. It's a massive number, as you will see. Now, here we go. That's our optimization, and that's the various conditions. As you can see, we have 5 of them. Let's start and by writing the Lagrangian function. And in this case, we have more than one inequality constraint. So we will have 3 lambdas, as we have a condition less than or equal 15, greater than 6, and less than or equal to 3. Now, this is going to be the general Lagrangian function, which is the function in x, y, z, the decision variables, lambda 1, lambda 2, and lambda 3, as you can see. Now, let's write the KKT condition for these constraints. Okay, here we go. The first 3 of them is going to be the non-negativity constraint. So x is greater than or equal to 0 will leave me with 2 inequalities and 1 equation, as we did previously. So for the non-negativity constraint, the derivative, I will differentiate the Lagrangian function with respect to x, y, and z. Putting x is greater than 0, y is greater than 0, z greater than 0, and then the multiplication will give me the inequality. So this is for the non-negativity constraints. As you can see, we have 6 inequalities and 3 equations. Now, going to the next constraint, which is the budget constraint. So for this less than inequality constraint, exactly like what we did previously, it will lead us to the derivative with respect to lambda 1 is greater than 0, and the lambda 1 is greater than 0, and the multiplication of lambda times the derivative of the Lagrangian function with respect to the lambda, the Lagrangian number 1, is going to equal to 0. I've wrote all of this as a remark beside it, and I've already sent you the PDFs previously. So for this less than or equality constraint, that's less than or equal 15, and this constraint sign is less than or equal, any increase in the availability V will result in an increase in the choice set, which results that the maximum will increase or stay the same. And all of this information we already did go through it in the previous session. Exactly in a similar manner, but remark the difference in the sign of the inequality of this constraint. So it's going to come up to the derivative of Lagrangian with respect to lambda 2. Lambda 2 is less than or equal to 0. Here's why, because related to the space, but I don't want to lose your concentration with me at the time being. So I'm just following the rules. So, and that's the last one, which is exactly like number 3. Here you can see it's a massive number of inequalities and equations. So once more, here it is. We have 1, 2, 3, 4, 5, and 6. We have 6 rows, which means we have 12 inequalities and the 6 equations, as you can see. So remarking that the confirmation or the construction of this system, we will have the following. As I told you, we have this huge number of inequalities, and that's the number of equations that involves in a similar manner. This is A for column A, column B, and column C, and they are marked 1, 2, 3, 4, 5, and 6 to the easy access for any equation or any inequality that we will see. Okay, that's a system of 12 inequalities, 6 equations, as I told you. It's one beautiful modeling problem describing the situation. The second step is to know how we are going to solve a system like this, which is really very simple. Solving this system is hard and difficult to handle. Let's use a hunch that maybe will help us, or maybe some information from their scenario. So let's open our ears again once more and see how these guys are talking or what they are talking about. Here is the summary of what we have. We have these equations, which and the inequalities. We already made the derivative of the Lagrangian function with respect to its decision variables, with respect to lambda 1, lambda 2, lambda 3, and we already formed our stuff. Once more, before we proceed, for you to remember, X is the number of vouchers, Y the number of emails, and Z the number of players. Paulo, okay, the devil here, it seems he's continue, and he said that it seems to me we will not need to hand vouchers. Please be careful about each word. We don't need to hand vouchers, and we will use the entire budget for these strategies, and we will ensure they work using a few resources as we can. Let's repeat this once more. First of all, we'll not need to hand vouchers. We'll need not to hand vouchers, which means X is equal to 0, because X is the number of vouchers. And we will use the entire, as I told you, that's the piece of information that we tried to sneak in to just write it. So X is equal to 0. There will be number of vouchers equal to 0. Let's get rid of this one. Okay, he continue. We will use the entire budget for these strategies. That means the budget will be used for the remaining ones. That's the whole strategy, which is X plus 2y plus 3z equal 15. And finally, we will ensure they work using a few resources as we can. So we need y plus z equal to 6. So this is the 3 information that we will depend on in hacking the system, and with some luck. So once more, x is equal to 0, x plus 2y3z is 15, and the last one, y plus z is equal to 6. Let's look at these conditions carefully. From the last one, y plus z equal to 6, it means z equal to 6 minus y. So inserting 6 minus y in the second row, as you can see how am I close to the screen describing what's happening. Okay, now I will have to make this substitution, as you can see. So making this substitution from the second row will develop a relation in y, which is the key solution here. I have 2y plus 18 minus 3y equal 15. X is equal to 0 given from the beginning. It's 6 minus y. So from the second row, I can get now that y is known, which is going to be y equal to 3. Once inserting y equal to 3 here, you will get z equal to 3. And you have x equal to 0. So now I have 0, 3, and 3. Taking all of this from this, Result, we found out that x is already satisfying the condition, it's less than 3, and y is greater than 0, and z is greater than 0. So the conditions of the inequalities are okay. We'll take this information, the value of 0.3, and we'll go first to 6c. Let's take this information and go to the 6c equation, which will develop that x equal to 0, which means lambda 3 times 3 is equal to 0. That's lambda 3 is equal to 0. Now I have lambda 3 is equal to 0 together with these conditions. We'll go to 2c. If we make a substitution in 2c, having the value of y equal to 3, the value of z is equal to 3, the value of lambda 3 is equal to 0, we will have the following two equations, which will all updated equations in 2c and 3c. And now I can get to the bottom of it. Lambda 1 is equal to 2, lambda 2 is negative 3, and the lambda 3 is equal to 0. From these values, now we hacked the system. A probable solution for it. X, y, and z, 0, 3. Lambda 1 is equal to 2. Lambda 2 is equal to negative 3. And the last one is equal to 0, which is lambda 3. All I have to do now, as exactly we did previously, we check this solution with the KKT condition. Okay, very good. Let's check. So once more, that's the system, ABC, and we have 6 inequalities. Six rows involving the inequalities and the constraints, and it's all satisfied beautifully. So the solution is satisfying the system, but we don't know if there is another solution or not. To the coming slides will be dedicated for this issue. So we will need now to speak about something really very important, which is the sufficiency theorem. In optimization, the sufficiency theorem provides conditions under which a solution that satisfies the KKT condition is guaranteed to be a global or local optimum for our problem. Reading this paragraph is really very important. It will summarize everything. I did try to make it as a statement. We will see it after we read it. I will stick with the objective function with maximization to avoid any probable complications from mixing the maximization and minimization together. And this, of course, this paragraph is from the main slides. So in the objective function of maximization, the problem B is differentiable. This is number one. And strictly or not concave. And the function of its constraints are differentiables. So the constraints also, or the functions of the constraints are differentiable. With lower than or equal or greater than or equal will make no difference, or equal constraints, it's all the same. Respectively, for the less than or equal, for the greater than or equal, for the lower than or equal to be convex, the greater than or equal to be concave, then any solution of its KKT condition is excluding the Lagrangian and excluding the Lagrangian multipliers that involve, it's a strict or just only a global maximizer of B. So let's move this into just bolts or points. So for an objective function in the maximization problem case, it means concave, either strict or not, to make no difference. The constraints of less than or equal, which is convex. The constraint greater than or equal, which is concave. The equality constraint, they not to be concave or convex. So this is the formulation of the objective function regarding the constraints, and I will depend on these 2 points in checking the sufficiency theory, as you will see. Any point that satisfies the KKT condition is a strict global maximizer. Same also will go for the minimization case. The objective function is minimum problem, convex, either strict or not, the constraints of convex and concave type, the equality, we don't matter about their case. Any point that satisfies the KKT condition is a strict global minimum. Okay, once more to this example or the first example. Let's consider this problem and try the KKT condition. Okay, that's another very nice problem, which also you can. This is really very close to the problem that we will see tomorrow, inshallah, in our overall revision about our course. It's very important session, and it's going to be a long one. I will try to partition it in more than one video, and I will give it tomorrow, inshallah. So now for the objective function, which is 20 minus x minus 5 to the power of 2 minus y minus 4 to the power of 2, subject to these constraints, non-negativity constraints, and this guy here, which is x plus y is greater than or equal to 3. Now that's the Lagrangian function. We form it, which is 20 minus x minus 5 to the power of 2 minus y minus 4 to the power of 2 plus lambda 3 minus x minus y. The Lagrangian the derivative of the Lagrangian function with respect to x, since we have non-negativity, now we are sure how to handle it. X is greater than or equal to 0. The multiplication is 0. Same goes for y. And finally, for lambda, we will have this equation exactly like what we formed previously. We have less than or equal constraint. So this is the derivative. We didn't go through the details of this. So for the first equation, I will start to differentiate with respect to x. I'm writing it in front of you. The second one and the third one. Remark these are greater than or equal to 0, less than or equal to 0 sign, less than or equal to 0 sign. It's just a minor typo here, and I will correct it. Okay, then I have x is greater than or equal to 0, y is greater than or equal to 0. These are the 1, 2, 3, and the ABC equation or the system. If we consider x is greater than 0, so from 1, okay, let's go from 1c. Now we can get that x minus 10 plus lambda is equal to 0. That's lambda equal to 10 minus 2x. And also considering y is greater than 0, so from 2c, I will get that lambda is equal to 8 minus 2y. Now from 3c, which states that lambda is greater than 0, so we will have now 3 minus x minus y is equal to 0, which means x is equal to 3 minus y. From these two guys, that means 10 minus 2x equal 8 minus 2y. And now I will make a substitution, replacing x by 3 minus y. Voila, I have just only one equation in y. So solving this guy will develop the value of y equal to 1. Once we know y equal to 1, so I will insert it here, getting the value of lambda. And also we will have the value of x. So y is equal to 1. Once y is equal to 1, just insert it here, x equal to 3 minus y, so x is equal to 2. Both of them together in either this equation or that equation will develop lambda equal to 6. Now we solve the system. And the decision variables are 2, 1, 2 and 1. And the value of lambda is equal to 6. Now come to the point of the sufficiency. Let's apply the sufficiency conditions here. So 216 is a solution for the problem obtained from its KKT conditions. Let's see how the sufficiency theory is applied. It's very, very simple. Step number 1, the objective function we have is already a polynomial type, so it is differentiable up to infinity. Contivity, we try to get the first partial derivative of this objective function, we will have it. If you are interested, we can put the gradient vector equal to 0. We will have another point, which is 5 and 4. But 5 and 4, it's 5 plus 4 is going to be 9, which actually exists not one of the visible solution. It's a visible solution if it is not an constrained problem. But we have a constraint here, and it's not satisfied, so I will ignore it. Getting the Hessian matrix, so the second derivatives. This is the second derivative for x. This is the mixed derivatives, and this is the second derivative of y. And to get the leading principal minors for this Hessian matrix, which is going to be a negative and 4, leading you to strictly concave, which supports our case for the time being. So that's a check one. We already have within for our objective function a point of optimality. For the constraints, they are also equations, polynomials, so it is differentiable everywhere. There is no problem. They are of the convex type because you have less than or equal inequalities. So it is the second condition sufficiently exists. So the sufficiency theorem applies in a strict form to R, which means that 216 is a strict global maximizer for our problem, as we can see. We went to example number 2, which is x squared y squared for xy is greater than 0 and xy is less than 2. I will have the objective function, which is a polynomial, and of course differentiable. Same applies to it. If we get 0 and 0, that's the solution, although it's satisfying. But let's get to the Hessian matrix. And according to the leading principle, it's a positive definite, which means it's strictly convex. I'm sorry. And this is not correct for our problem. We are handling a maximization, so it's not concave, which means that the sufficiency theory doesn't apply to this problem. So maximization problem, it should be concave, not convex. So now we can't apply that theory here. Let's remember that this problem has two solutions. We already solved this problem previously. We have, in the previous session, we have a detailed solution graphically for this problem. If you remember the circles, and it is a paraboloid, and we did solve it and go through in details. You will find the details of the solution in the previous session. So let's remember that the solution is 2 and 0 and 0 and 2. These are the maximization points. But for the KKT, it gives me 0, 0, 0, 2, 2, 0, and 1 on 1, as you will see. So these are the points 0, 0, 0, 2, 2, 0, 1 on 1. And some of them are minimizers or maximizers. Since the sufficiency is applied to this problem, we simply cannot confirm or reject the case. Okay. Once more, let's try the sufficiency situation theorem for the problem of the directors that we tackled before. So now we have the objective function, which is negative x squared, xy, blah, 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 subject to these constraints, the non-negativity constraint and the inequality constraint, which are 0, 3, 3, 2, negative 3, and 0. We already solved them just seconds ago. Lois' question related to this point, are you sure that the solution of these conditions are found corresponds to the solution of our problem? That's the comment on the final solution of the strategies. Step 1, let's look to the objective function, which is a polynomial, so it is differentiable in everywhere. The gradient vector is concavity, getting from it the Hessian matrix, which is also strictly concave, which informs that we are having a maximization problem, and it's all well set. The constraints are these are G1, G2, G3 for the constraints, and they are differentiable, all of them, and they are linear. G1 and G3 are convex, and G2 is concave. So sufficiently theorem is applied, and everything's perfect. So it's a global maximizer. We'll need to speak with you about the regularity condition of the problems, of our problems, as it is the introduction to our necessity theorem. So we have the sufficiency, and we will go through the necessity condition now. So all constraint functions are linear, and this is one of the regularity conditions we need. Was the choice set had the following regularity conditions: convexity, the lower than or equal, greater than or equal constraints functions of V are respectively convex and concave. We already saw this also, and this will be applied on the simple problem of the example that we tackled before. The gradient vector x is convex and has at least one interior point, and if A is boundary point of x, no gradient vector involved of A of this binding on the edges. I'm sorry, on the binding edges of our visible area of solution. The linear independence, if A is bounded point of X, then the gradient vector involved at A, the function and the constraint, which are binding for a linearly independent set. This is going to be checked as we can see. Now, it is enough for the necessity theorem states that at least one regularity condition, one out of these four, of an optimization problem is satisfied, and the qualification constraints in optimization problem is also satisfied, and so any extreme point of V is together with certain Lagrange multipliers a solution set of the KKT condition. That's the sufficiency theory and the necessity theory. So if we want to apply this, the qualification constraint is very difficult to verify. It's very simple to check any of these conditions. At least one of these four regular conditions on the constraints, it will be enough to have a qualified constraint. Back to our problems once more. If you remember this problem, x squared subject to this bunch of constraints. First of all, the linearity, all the constraints are linear, so it is satisfied. We don't need to go further, but we will check all the requirements. The constraints of this function is linear, of this objective function is linear. That's the x is greater than or equal to 0, y is greater than or equal to 0 constraint, and that's the bound of x plus y is equal to 2. All the points within this triangle is satisfying this constraint. So J is linear, it is satisfied. Conclusion, necessity condition applies to P, and the point that we will have is an optimal point from the KKT condition. We want to check the convexity of lower than or equal and greater than or equal constraint. Any point that's within this area is approving the constraint, which is an inequality constraint, less than or equal, so it's a convex type. So once more, the necessity theorem applies to P, and we have a solution for the Karushkuhn-Tucker conditions. The gradient vector of x and has at least one interior point of A is bounded point on the set. So no gradient vector evaluated on the function of the constraints. So now to check all of this, we have the gradient vector already exists at the point 1 and 1, which is inside and it's not null. So this condition is satisfied also. As I told you, just only one condition is enough. And for the linear independence, if we took every two edges or every 2 points and from the corners, and we try to get the binding function or the binding constraint, we will have the linear independence rank, which is 2, equal to the number of constraints at this point. So they are linearly independent. And so on. I will do it at B, at C, at D, and F. All of this, you will find the details of this analysis in the main slide. So it's exactly the same as I told you. We don't have to go through all of this. It's enough for us just only one condition out of these four constraints. For example, two, let's check. That's the objective function, our objective function, and these are the constraints. And once more, as you can see from all of this, Pedro, I know that we already solved the problem, but it is not possible that there are other solutions. That's the information of the necessity conditions. This is J1, J2, and J3. These are the constraints that we have. All of them are linear. So the solution of the KKT is sufficient for us, and it is a maximizer for our problem under these constraints. So we are all set. Sufficiency and necessity and the solution of KKT. If between the sufficiency and the necessity theorem, at least one of them applies to our optimization problem, the resolution of its KKT condition allows to solve our problem. So here's the problem. Here is the xy, and the xy is less than or equal to 2. According to this one, we have we now know we have an extremum point. So Weierstrass theorem stresses that we have a global maximizer, or ensures that we have a global maximizer. The KKT condition supported the possible solutions. Not sure it will exist or not. Sufficiency theorem, it was not applied here successfully. So maybe not maximizers or maybe a maximizer. Of course, the KKT is applied to all constraints are linear, so necessity condition theorem is applied. Finally, the highest and lowest images informs our solution of maximizing and minimizing. So at 0, 0, the value is 0. At 4, 2, 0, 0, 2 is 4. At 1, 1 is equal to 2. So we have 0, 0 a minimizer, 2 and 0 and 0, 2 are global maximum of B. It's confirmed, and that's the relation as I told you. Sufficiency theory and the necessity and KKT. Also, once more for this problem, the director's problem, we subject to these constraints. This is the solution. Sufficient theorem is applied, necessity is applied, so it is a global maximizer for our problem. Now I will come to or tackle the one and the important part of our problem in general, which is the analysis of the sensitivity analysis. We need to know after solving any problem and having the optimal solution after all of this suffer, going through the equations, the formulation of the KKT, solving the system of equation, that we are not under, and as I told you, these are just only simple problems. But if you have more complicated problems, it's going to be a way difficult than this. So this is why we need the sensitivity analysis to be successful and to be applied. We need to know after solving the problem and having the optimal solution, what will happen if a parameter of the objective function or the binding constraints it changes. What's the corresponding change in the optimal solution then? So this is really very important. If one of the parameters of after solving our problems changes, what's gonna be the effect on the optimal solution that we already have? Okay, according to the envelope theorem, the derivative of the function, which turns for each value of a parameter alpha, the extremum of an optimization problem B with differentiable function is the same as the derivative of its Lagrangian function with respect to this parameter. Okay, let's see. If I have this problem, which we have already several times, we already solved it, and we have the optimal solution, which may happen at 2 and 0, 0 and 2, and the global maximum is 4. Let's see if we have some changes in this model. So, if the objective function changed to be on the following form, لو أنا عملت تغيير في objective function, if we make a change in the objective function, let's say we will multiply the value of the objective function by 0.9. So my parameter here is alpha, which is 0.9. And same constraints, same everything. The global maximizer or the maximum, what's going to happen to it? So instead of dealing with x squared plus y squared, I will deal with alternatively 0.9 x squared plus y squared. Let's estimate the change corresponding to this situation. So now I will have alpha times x squared plus y squared, which is plus lambda 2 minus x minus 1. Differentiating the Lagrangian function with respect to alpha will develop x squared plus y squared. And at the critical point or at the solution point, for the previous value of alpha, which is 1, and the solution set, which is 0, 2, and 4, okay, I will get the following. That's at 2, 0, and 4, or 0, 2, and 4, the optimal is equal to 4. Now, I will change the maximum. Remember, I've given you this equation previously, which define the percentage of a change that will happen or will cause a change in our optimal problem or optimal solution. So all I have to do is to get the derivative of n with respect to alpha, and then multiply by the difference, which is new alpha minus the old one, 0.9 minus 1, which is going to be minus 0.1 times the value 4, which is the value relative to the optimal solution. So the optimal function will, due to the change or reduction in using alpha 0.9 instead of 1, the optimal value will be decreased by minus 0.4. So now at 0.9, alpha 0.9, will cause that the global maximum will be decreasing by 3.6. It's a very good example to see how the envelope theory works. Let's see the envelope theory on the sports club director. Okay, here's the objective function, that's the constraints, and this is the solution that we already have. Okay, Lois stated that I'm so excited with these strategies that I'm considering to increase its budget in 5M euros next year. But if we do that, we will have less money to invest in the team and we will get 9 less points based on the quality of the team that we did this year. Is it worth it? Let's check that. Step number one, the new Lagrangian function. The new Lagrangian function is not going to be 15. It's going to be alpha minus x minus 2y minus 3z, which will develop the new Lagrangian function. If we differentiate the new Lagrangian function with respect to alpha, then we will get lambda 1. So lambda 1 value is equal to 2 from our solution. So now we have the value of lambda 1. Changing the maximum, so we have the value of the optimal function, which already know at the time being, and the amount of the change, which is 5. So multiplying them together, it's going to equal to. Now, writing the equation due to this increased conclusion from which is going to be 10 greater than 9, they should increase the budget for the strategies. If you have any questions or any concerns, please send it to me, and we will be together tomorrow so we can negotiate this and we can discuss this in details, as we will say. Also, please visit the main slides on Moodle and try to solve this challenge. It's really very important. Once more, thank you very much for following us in this session. I hope you understood all the details. And once more, please try to go through it in depth. Try to resolve it again. It's really very important problem. We have a lot of information involved in this session. In order to digest it well, you will have to visit it more than once. Thank you very much for following me, and thank you very much for your hard work. Thank you, Nova, for this wonderful course, which connected a lot of things together between the depth of mathematics to the enrichment of the application through live problems and everything. So thank you all very much, and I wish you the best of everything. Thank you. Enjoy the rest of your day.